Lesson 5.2, Logarithmic Functions and Their Graphs. I know this is the same picture from 5.1, but I just wanted to check in with you to make sure that you recognize where the buttons are that you'll need for today. We're doing the inverse of exponential functions, so you're going to need to find the log and the ln button. They're pretty easy to see on the TI-30, but on the TI-34 you have to hit the second function and then the PRB button for probability. There you'll see log, you'll see ln, you'll see base 10 and base e. On a graphing calculator, you should be able to easily find the log and the ln buttons over on that left-hand side. To look at the inverse of an exponential function, let's first look at the graph of an exponential function. It says consider the graph of f of x equals 2 to the x power. That's over here on the right-hand side. That's f of x. Graph the inverse and write its equation. Well, the first thing we need to remember is the definition of inverse. The definition of inverse is the reflection over the line y equals x. So make sure that you draw that in, and then we'll take a look at sketching the graph. Notice the graph for f of x is already given, but what we want to do is create a table. That's actually how we graphed an inverse. If we start off with numbers that we know, we'll start off with something simple like 0, right in the middle of the graph. That means we're going to evaluate 2 to the 0 power, and that equals 1. If we plug in 1, 2 to the first power is 2. If we plug in 2, 2 squared is 4. And if we plug in 3, 2 cubed is 8. And then that's going to put us off of our graph. So if you look over at the right, those ordered pairs are already plotted for us. Let's go in the other direction. Let's do at least one that's negative. If we pick 2 to the negative 1 power, that's 0.5, or 1/2. And that's plotted on the right as well. Now, as we sketch the graph of the inverse, remember we just switched the ordered pairs around. So instead of 0, 1, we're going to have 1, 0. And then we'll have 2, 1, 4, 2, 8, 3, 0.5, negative 1. Pause the video and plot those coordinates, and then let's see what the shape of our graph looks like. You'll notice I zoomed in so that we could see where those points are plotted. It looks like if we folded the red, or the graph over that pink dashed line, the red would kind of match over to this green. Since the asymptote for our exponential function is the x-axis, the asymptote for our inverse is going to be the y-axis. So it kind of comes along here, connects through these points, and then turns over here to the right. And that's the inverse for that exponential function. And this is where the title of the lesson comes in. We're also asked to write the equation, which means find it algebraically. When we did this with linear functions, the first thing we did was we replaced f of x with y. So we wrote y equals. In this case, we'll have 2 to the x. Does anybody recall the second thing we did? Kind of like with our table, we just switched the x and the y around. And then the third step is where we actually get stuck. We're supposed to solve for y. And the thing is, when y is in the exponent, we can't really take the y root because it would still then be on the other side with x. So we're kind of stuck with y. I'm going to say y is stuck. We really can't get it by itself. Since there's an actual graph, we actually need to figure out how to generate an equation that models that graph. This is where we go down to the next row. It says the inverse of an exponential function is called a logarithmic function. And this hopefully sounds familiar to you from Algebra 2 last year. To write the equation, we do switch x and y like we did up above, but then I like to say that we loop the equation. We loop the equation using log as a prefix. So we're not going to write logarithmic every time we write this kind of equation. We're going to use log. So here's what I mean. We have y equals 2 to the x. I'm going to loop it, or not loop it, sorry. I'm going to switch x and y. So then I'll say x equals 2 to the y, just like we did before. And then I'm going to loop it using the prefix log. We literally start with that log prefix. Notice the base of our equation is 2, and that's going to be our little sub-base for the logarithm. So here's where the looping comes in. The 2 and the y are going to be on opposite sides of the equation for the inverse. So what comes next, we're going to take the log of x. So we write x kind of in the same level as the log. Notice the 2 is a little subset number. Then it's going to equal the exponent y, and that's going to be on the same level as well. So we read this, y equals log base 2 of x. That's how you'd say that equation. The definition of a common logarithmic function with base a. Y equals log base a of x if and only if the base to the exponent, so here's where we loop it again, a to the y power equals x. So that's just looping it in the other order. One thing to note for that a value, your base has to be greater than 0. And it can't equal 1. So there's a couple of rules for a. X also has to be greater than 0, whatever you're taking the logarithm of. So it says evaluating. Really what we're just going to do is convert. We're not going to actually evaluate. So we can even get rid of that right there. To convert from one form to the other, we're just going to do that looping. If it's exponential and we want to convert it to logarithmic, we start with that log prefix. So we just write log. Notice in 2 to the 3rd power equals 8, the base is 2. So that's going to be the base for our logarithm. That will always be true. What are we taking the logarithm of? Here's where the looping comes in. We're going to split up the 8, or put the 8 on the left. Sorry, I don't know why I said split up the 8. Log base 2 of 8, and what it's going to equal is the exponent of 3. So the exponent will always be on the opposite side when you take the inverse. And that's it. That's all you do to convert. Try the next one. 4 to the negative 2 power is equal to 1/16. To write this in logarithmic form, we write the prefix log. Our base is 4, so we're going to write that little sub 4. What are we taking the logarithm of? That's where we loop it. 1/16. I'll put that in a parenthesis. What will that equal? If we loop it back to the exponent, it will equal negative 2. So we're just writing equivalent statements from exponential form to its logarithmic form. Last one, m to the r power equals g. Doesn't matter what our numbers or variables are. We're going to start with the prefix log for logarithm. Now our base is an m because it has the exponent. So we'll write that little sub m. What are we taking the logarithm of? Of g on the right-hand side. What should it equal when we're done? If we loop it back, it will equal r. So that looks kind of strange, but log base m of g equals r. Next, we're asked to convert from logarithmic back to exponential. Whoops, I wanted a different color for that. Hang on. Back to exponential. There we go. So log base 3 of 9 is 2. What you want to do here is now not use log in your answer. You want to start with your base. In this first example, the base is 3. So I'm going to take that and just write it kind of in its own plain row. Now remember, we separated the base from the exponent before, so now we need to put them back together. And that's where looping comes in. If we raise 3 to the 2nd power, guess what it equals? It equals 9. And there's your exponential form for that logarithmic statement. All right, the next one. Log base b of 8 is 4. Here the base is b. We're going to raise it to the 4th power, so grouping the base and the exponent back together. What should that equal when we're done? It should equal 8. And there's your exponential form. All right, last one. Log base 5 of 1/25 equals negative 3. Our base is 5, so when we're writing it in exponential form, we eliminate the log and we start with the 5. We're going to raise that to the negative 3 power to group those two back together. 5 to the negative 3, it equals 1 over 125. And that's all you do to convert from one form to the other. All right, let's grab our calculators. So it says use a calculator with common logarithms. Logarithms have lots of different types of number or variable bases. If the base is 10, you can use a calculator to approximate. but only if it's base 10. Typically, a base 10 is written without the 10 in the equation. So instead of log base 10 of 13, it's just log 13. If they don't have a number base written right here, 10 is implied. And that allows you to use your calculator. So you literally find that log button on your calculator and press it so it's on your screen. And then you take the log of whatever you want. So ultimately you're evaluating 10 to what power equals that number. So let's try with log 13. If you type log 13 in on your calculator, 13 isn't much bigger than 10. So the exponent won't be a whole lot bigger than 1. If we evaluate to 4 decimal places, you get approximately 1.1139. Here's a great way to check this. Since this is the inverse of an exponential function, if you type 10 to the 1.1139 power, guess what? You'll get approximately 13. So we're just showing you the different form for that exponential function. All right, the next one, log of 432.12. Our answer should be bigger since this number is bigger than 13, obviously. So if we type in log 432.12 on our calculator, we're going to get approximately 2.6356. So if we took 10 to that power, we'd get approximately 432.12. If we try the next one, log of negative 19, you're going to get an error on your calculator, or no solution, not possible. This is because, remember, that number has to be greater than 0. We can't have negatives. If you're ever asked to evaluate the log of a negative number, you always know it's going to be no solution, or an error. However you want to state that is fine. Can't have negatives. Okay, and then the last one, log of 1. Cute, 1. Type in log of 1. That actually equals 0. We don't have to round because it's exactly 0. And this is true because 10 to the 0 power equals 1. We have lots of properties related to logarithms. A couple of them we've kind of already talked about. The first one says log base A of 1 is 0. So anytime you have 1 that you're evaluating the logarithm of, I should put that closer to where the arrow should be. There we go. Anytime you have a 1 that you're evaluating, the answer is always 0. In that second property, anytime you have the same base as what you're taking the log of, that always equals 1. If you have a logarithm that has the base the same as what you're taking the logarithm of, they cancel out and you just get x, whatever the exponent is. That also works if you have a base raised to a logarithm that has the same base. Those still cancel out and you get x. I know, these are kind of unique looking properties. And last but not least, if you have an equation with a logarithm on each side, if the base is the same, you can essentially eliminate the logarithm prefix and just solve the equation for whatever you're taking the logarithm of. Over on the right, it says simplify using properties of logarithms. Log base 4 of 1. Well, anytime you're taking the logarithm of 1, that's automatically going to be 0. That's a definition, so you don't even have to try to plug that into your calculator, which you couldn't do anyway since the base is 4. In the second one, log base 7 of 7. Again, anytime the base matches what you're taking the logarithm of, that answer is always 1. So we'll take those free points when we can get them. The last one, 12 to the log base 12 of x, since the base of the exponential equation is the same as the base for the logarithm exponent, they cancel each other out, and the answer is just x. I know, kind of surreal. Down below, we'll do some solving for x. It says use the one-to-one property to solve for x. In example A, log base 4 of 12 is equal to log base 4 of x plus 3. Since the logarithms have the same base, we can just say 12 is equal to x plus 3. To get x by itself, we'll move 3 over by subtracting, and x equals 9. All right, you guys try the next one. See how easy this one-to-one property is. Notice if it's log base 3 of x is equal to log base 3 of 14. Since the bases are the same, we eliminate the logarithm term, and x automatically equals 14. For this last one, log base 4 of x squared minus 6 is equal to log base 4 of 10. Once again, since the bases match, the logarithm term essentially goes away, and we can solve the quadratic. Let's see. X squared minus 6 is equal to 10. No fear, if we move 6 over, we isolate our x squared term, and we get 16. To take the square root of 16, I'm going to put a big star right here. Remember this, everybody. We have to put plus or minus out in front, and 16 is a perfect square. That equals 4. So there are two possible solutions for x for this final answer. So far, all of our bases have been number values, and we've used that common logarithm log. But if you recall from lesson 5.1, we had a natural base e, which will also have an inverse, and that's called a natural logarithm. So if your base is e, the inverse of y equals e to the x would start off by switching x and y and looping it. But when we loop it, we're not looping it with log, we're actually going to loop it with ln. And we say ln of base e of x is equal to y. But here's the thing. ln only works for base e. It only works for those natural logarithms only work for base e. So kind of like common log base 10 when you type it into your calculator, we don't need the e in our equation. So we'll say y equals ln x. And I'm just going to write here always and only base e. So we won't have to worry about base 4 or base 7 or base 3. It's always base e when we use ln. And recognize, you guys, it's ln. It kind of looks like in, but it's ln for natural logarithm. It says use the ln or find the ln function on your calculator and use it to evaluate to 4 decimal places. Kind of like log when it defaulted to base 10. Anytime you have ln, we know the base is automatically e. And you can just find the ln and get that to show up on your calculator. To take the ln of 2, you're going to figure out, sorry, I have to put my paper over here. To figure out the ln of 2, you actually get a decimal to 4 places, 0.6931. That's approximately, I'll throw a little squiggly equals in there. There we go. Oops, I'm on the kind of too close to the edge of my screen here. So we're just going to put a squiggly equals on this side. That'll work. If my screen will work. There we go. There. Approximately 0.6931. ln of 0.3 is going to be even smaller. This is actually going to be a negative answer. So here's the thing, you guys. You can get a negative answer for an ln expression. We just can't take the ln of a negative number. So negative 1.2040 is a valid solution. But in example C, ln of negative 1, if you try typing that in, again, we get an error because of the negative. Remember that we can't take the ln of a negative number. Can't take negatives. There we go. Up above, we had common logarithm properties. Down here, we have natural logarithm properties. And you'll notice they're very similar. They kind of match up in order, just like the logarithms up above. ln of 1 equals 0, just like log of 1 equals 0. So that's always going to be a match. ln of e is already a base e, so it's kind of like those two are the same anyway, and that automatically equals 1. Anytime you raise e to an exponent, but you evaluate the ln of it, it's going to be the same number. And again, if you have e as your base, that matches the base of the ln, so your answer is going to be x again, just like it was up above. That's that weird inverse property. If you have ln's on each side of the equation, you can just solve what you're taking the ln of, similar to what we did up above. It says simplify using properties of natural logarithms. ln of e, again, that automatically equals 1. That's pretty easy. Here we have e to the ln of 5. So since ln is automatically base e, they just cancel out, and your answer is automatically 5. Last but not least, ln of e to the 8th. Again, since ln is base e, the e's cancel out, and you just get 8. So some of those properties should go pretty quickly. Flip it over to the next page and we've got an application problem for these. All right. The nice thing about these application problems, everybody, is you're going to be given the equation. We don't have to generate it. We just have to plug things in, kind of like the tiger shark problem in 5.1. It says students participating in a psych experiment attended several lectures on a subject and took an exam. Every month for a year after the exam, the students took a retest to see how much material they remembered. Averaging the scores gave them a human memory model f of t equals 75 minus 6 times the natural log of t plus 1, where t is anything from 0 to 12, which would be the months in which the students took those tests. Question A, what is the average score from the original exam, meaning t equals 0? If we plug that in, we would get f of 0 equals 75 minus 6 ln 0 plus 1. Now you should be able to type that all in at once on your calculator. 75 minus 6 ln, well 0 plus 1 is in fact 1, and you actually get 75. So 75 was the average initially. For example, B, I'm going to drop B down here. In 2 months, what do you think is going to happen? Do you think that they're going to remember more of the content or less of the content? Typically, it would make sense that they may not remember quite as much. So let's see if we plug in 2 for t, what happens to that output? F of 2 equals 75 minus 6 ln 2 plus 1. You should be able to type that all in at once. 2 plus 1 is 3, so you could condense that much down. Notice there aren't any parentheses, so just type it all in at once. And I found to the nearest hundredth that the scores did in fact drop a little bit. I got approximately 68.41. So in a couple of months, students lost some of the retention of that content. For C, after 6 months, it would be expected that it's probably lower yet. So let's evaluate. F of 6. 75 minus 6 times ln 6 plus 1. So 6 plus 1 is 7. And again, if you type that all in at once, we get approximately 63.32. So the trend of the data over time seems to be dropping. And that's utilizing a little bit of exponents and logarithms in application. There's lesson 5.2.